So with piecewise defined functions, there's a listing of all functions, or not all functions, but a lot of the ones that we'll deal with in here in the textbook in section 3.4. I'll try to send a PDF tomorrow with that, or tonight before I leave here, with some of those functions in there. But in the textbook, there's a listing of those functions. Not necessarily something you have to memorize, but just be familiar with the basic idea of an x squared function or x cubed function. That idea is what that's all about. And we're going to use parts of those with piecewise defined functions as we build those up. So we're going to be using some of those pieces in our piecewise defined function. So I'll send a PDF probably either tonight or tomorrow with that stuff involved in case maybe it's a little more condensed place of looking at it. So piecewise defined functions. A piecewise function it has parts, and I'm just going to call that part A, and then they'll list you a domain for part A, and they'll tell you what x's that works for. And then they'll have a part B, and then they'll list the domain that part B applies to. And then it might have a part C, and then they would list the domain for that. Okay, so they're going to tell you the domain for each part. And what we've got to do, excuse me, with piecewise defined functions is take those pieces, draw us a graph from that, or develop, whatever they ask as a function value for. We got to know which part to go into to get our function value out of that. And so sometimes there's 2 parts, sometimes there's 3. I've seen some with 5 or 6 parts, but it's all kind of based on that. Okay. All right. So looking at piecewise defined functions, the first one we're going to look at, just a first example. Stay pretty simple with it, and let's just use linear pieces like 3x plus 2, 6, and then negative 2x. And the domain for that first piece is going to be all x's that are less than negative 2. And for the second piece, it's going to be from negative 2 is less than or equal to x is less than or equal to 4. And for the third part, it's going to be when x is greater than 4. Okay. So those are the pieces that we're going to build our function from. So I'm going to get it real quick so I can draw some straight lines. All right, so I'm going to graph this first, and that's going to help us kind of answer some questions about this. So I'm going to draw myself a coordinate plane, and I'll show you how you can use the graphing calculator to help you get an idea of what's going on. Some too. Let that be opening up. All right, so I'm going to graph that first piece, and it says it's 3x plus 2, but only when x is less than negative 2. So what we've got to do to graph that is find those important points. Okay, those important points are going to be the x values that are pointed out in our domain. So there's an important point at negative 2 as an x value. So if I plug in negative 2 into this equation here, 3x plus 2, that's 3 times negative 2 is negative 6 plus 2 would be negative 4. That means at that point, that's the right-hand end of that particular part of the graph. So we would go to that point, negative 2, negative 4. We're going to put an open circle because it doesn't have the equal to mark. Okay, equal to mark, open circle. No equal to mark means open circle. If it has an equal to mark, we're going to put a filled in dot there. Okay, so for this one, it's an open circle, but it fits the equation 3x plus 2 for everything that's less than negative 2. So that means that direction. Okay, All right, so slope was 3. So I'll go down 3, left 1, down 3, left 1. Graphing a line, that's all I'm doing right there. That line, 3x plus 2. But it's only to the left of that point because it said all x's that are less than -2. So that's why I'm going everything this direction. Okay. All right. So that gets us the first piece. The second piece occurs from -2 to +4 on the x values. And the y value is the equation for y equals 6, or f of x equals 6. So it has 2 important points. One of them is at -2, 6, and the other one is at 4, 6. I get 6 on both of those because that says no matter what x is, I get 6 for y. That's what that says. Okay. So then I take those 2 points, and they both have equal to marks on them in the inequality, the -2 and the 4. So I'm going to put filled in dots on those ordered pairs. So -2, +6, 2, 4, 6. And then +4, +6. So filled in dots there. And then y equals 6 is a horizontal line at that number. That's the middle piece. That's what it looks like. And then we're going to graph the last piece. It has an important point at 4, and then we plug that into x. 4 times -2 is -8, so 4, -8 is the important point for that one. Is it an open circle or a filled-in dot? Open, because we don't have an equal to mark. Okay, so we're going to go to 4, -8. Open circle. And then it follows the graph of -2x from there on. So that's a linear equation, -2x, so it has a slope of -2. So I can take that and go down 2 over 1. And it follows that pattern the rest of the way from there. Okay. So we get the graph of that piecewise defined function. Looks like what we're seeing right there. Okay. Now, we're going to answer some questions about this one. We're going to tell the domain of the whole function and get the range of the whole function. We're going to get the intercepts for that function. And then we're going to talk about this thing called continuity. Okay. All right. Domain. Domain deals with the x values. The great thing is you get all these domain pieces given to you over here. So that's going to help us know what the domain is. It says it goes from -∞ up to -2 and then stops. But then the next piece picks up at -2, goes all the way to 4 and stops, including 4. So far, we've gone from -∞ all the way up to 4. We've taken care of every number. There's not been any that have been left out. Because this one stopped but didn't include -2, but the second one picked it up and said, oh, I'm going to use that -2 that you didn't use. Doesn't always happen that way. Sometimes they do skip some numbers. They didn't on this one. Okay? We're up here at 4. This says for x is greater than 4. So this one used 4. This one doesn't, but that's okay. It means 4 was used. And we're going up from there to +∞. So the domain for this one happens to catch every number from -∞ to +∞. We don't have to have the graph to find the domain. That's what I want you to know. The range, the graph is very helpful in finding the range. Okay? We look at that range. Range is the y value, so that's up and down. Okay? We look at that. When you read a graph for the range, you want to start at the bottom of the graph. Okay? What are both of these doing? Going which direction? Down. Toward what? If I keep going down with y, that's going to be toward what? -∞. So my range starts at -∞. And both of these are going here. This one stops sooner, so I'm going to start there. and it goes up here, and that y value was -8. But -8 was used as a y value over here, so I can keep going. I can jump over here and keep going up. Right there's a spot where the y values stop happening for a minute. What is that y value? -4. We're going to skip some y values because there's all this empty space in this area. There's all that empty space that's happening there. There are no y values being used from -4 up to what y value? 6. That one is used. This one has a range from -infinity up to -4. Then it skips all of these and then uses only 6 for the rest of that spot. And that's as high as our range goes. Doesn't go any higher than that. Okay, so we get the range. The graph is very useful in finding the range. It's always a helpful thing. Okay. Intercepts. What kind of intercepts are we looking for? What kind of intercepts exist in graphs? This one doesn't necessarily have to happen, but there's two kinds. X and Y intercepts, okay? So we're looking for places the graph crosses the x-axis or the y-axis. We need to find both of those, okay? All right, so does it cross the x-axis? Anywhere? Nowhere. So we're not going to have anything there. No x-intercepts. Where's it crossing the y-axis? At 6. What's the ordered pair that it's crossing the y-axis at? 0, 6. That is the only intercept we have for this particular graph. There are some graphs that don't have any intercepts, and that's okay. It's not necessarily bad, good in any way. The last thing we're going to talk about with piecewise there is continuity. Continuity deals with how if the graph is continuous or not. And kind of the best way that I can describe continuity to you is, can you start tracing the graph and never pick up your finger to draw it? So if I trace this one, if I start here on the left, do I have to pick up my finger to get to the next place? Yes. If I have to pick up my finger, it's discontinuous. If I can draw the graph and never skip any spots or have to pick up my finger to move to another spot, then it's continuous. This one is discontinuous. Most, not all, but most piecewise functions are discontinuous. Not all of them, but most of them, okay? So this one we would say is discontinuous because we cannot keep going from left to right all the way across the graph without picking up our pencil or finger as we trace it. That's kind of how you want to check your continuous and discontinuous stuff. All right. Show you a little bit with the graphing calculator how you can get a little help with that. So on the graphing calculator, you can graph these piecewise as 3 individual pieces. So if you put each piece in parentheses, so I'm going to put 3x plus 2 in parentheses. And then another set of parentheses, I'm going to put the domain for that. And the domain for this one was x is less than -2. So I'm going to hit X, and then I'm going to hit second math. And it should give me these inequality symbol. Second math to get there. And it says less than, so that's option 5, -2. Okay. If I hit graph right here, we should see, here's that little piece that we got there. It doesn't put the little circle on the end like we did when we drew it by hand, but this is that little piece. This right here just says, okay, we're not using the rest of these x's. That's what that means, okay? So we'll go to Y2, and we're going to put in the second piece, which was just a 6. And this one is a little tougher to do because you can't put in a compound inequality graphic calculator. You have to do two individuals. And the way you want to think about that, it says -2 is less than or equal to x is less than or equal to 4. So what you've got to do is split that apart into x is greater than or equal to -2 and x is less than or equal to 4. That's what we have to put into our calculator. So to do that, you're going to hit x second math less than or equal to, oh, excuse me, greater than or equal to. We're going to do the -2 first. Greater than or equal to is 4. -2. And then I'm going to hit second math. Go over to logic. Math 140 right now. All right. And so second math, go over to logic to get and. All right. Get back down there to that. Put in the rest of that. X is less than or equal to 4. X, second math, less than or equal to 6, 4. Close those parentheses. All right. So here we have piece number 1. Here is piece number 2. Looks just like what we drew by hand. And then we need piece number 3. I'm going to put that in Y3. And it's -2x. Whoops, I need parentheses around that. Parentheses. 2x. Close parentheses. Another set of parentheses. And it says for x is greater than 4. X, second math. Graph. All right, so here we have our pieces. First piece, second piece. See the picture of that. I find it easier just to graph it by hand. Go through all that stuff. But it can be helpful to be able to do that with the calculator. Not necessarily required, but it is can sometimes be helpful. All right, let's look at another one. G of x. Let's just do a two-piece one this time. X squared for x's that are less than 2, and -3x plus 5 for x's that are greater than or equal to 2. We can go ahead and answer the domain part of this because we don't need the graph to get the domain. Well, read the domains over here. It starts at where? X is less than 2, so we would be going from where? -infinity, good. All the way up to 2, and then we're stopping there for the first piece. Second piece, where does it pick up at? At 2. So is 2 used? Yes. So we haven't skipped a number. We're using the 2 that we thought we might be skipping. Okay, and it goes to where? X is greater than or equal to 2, so it would go on up to where? Positive infinity. So the domain for this one, all real numbers from -infinity all the way to positive infinity. This one drops the 2, but the second function picks it up. So you leave any out. All right. Next thing to do is get the graph of that thing going so that we can look at the range. The graph is very helpful in finding the range. So that's what I'm going to do. This is where those important points come in when we go to graph it. So what x value is important for part 1, for the top function? Two, right? That's the only x value they told us about. They told us x's that are less than 2. 2 is an important spot because that's where things happen. So I'm going to plug in 2. If I plug in 2 for x in x squared, 2 squared is 4. So I end up with this ordered pair, 2 2, 4, and I go to that spot, and do I put an open circle or filled in dot? Open, because it's not equal to. All right. Now it says for everything where x is less than 2, so that's going to be this direction, it looks like x squared. So I'm going to plug in some x values that are less than 2 and get the picture of the graph. If I plug in, that point wrong. Got in a hurry there. There's 2, 4. Sorry. If I plug in 1 for x, what's 1 squared? 1. So there would be that point. If I plug in 0 for x, right there. If I plug in -1 for x, what's -1 squared? 1. If I plug in -2, 4. So we end up getting this picture going. It's a quadratic graph. That shape's called a parabola. So that's the piece that's there first. It's listed first. -infinity up to 2 looks like that. The next piece starts at 2. So that tells us there's an important point at 2 something for that particular graph. So what do I do with this 2 here? Plug it in, and that's going to give me -3 times 2 is -6 plus 5 is those are different. That's good enough. I guess it's the best we're going to get. All right, so -6 plus 5 is -1, right? So we go to that point, -2, -1. And we put it filled in or an open circle? Filled in, because it's got an equal to mark. And then it follows the graph of -3x plus 5 to the right. So I know that's linear, so I know I can count that slope down 3 over 1. If you don't know that, then you can just plug in x values that are greater than 2 and get some dots that kind of give you the picture of that. So if you end up with a function that's part of your piecewise that you don't know what it looks like, kind of goes back to that list that's in your book. Or there's actually a couple of boxes that it has where it lists all that stuff about them. You can just plug in x values and you'll get an idea of what the graph looks like. You'll get a basic shape of it, which is what we're really after here is basic shape. Down 3 over 1, I could keep doing that forever. Not gonna. So get this straight line that goes that way. Okay. So that helps us find the range. Remember, when we're finding range, we're going up and down. We're going to start at the bottom. What's the lowest y value that we see? -infinity. Because this keeps going down forever, our range is going to start at -infinity. Does it stop anywhere as we go up? It stops there at -1. Is -1 included? So we should put what on it? Bracket or parenthesis? Bracket. Included is a bracket. Parentheses is excluded. What's the next y value that's used? Okay. And that goes up to where? Infinity, because this side of that line goes up forever. So that's right where our positive infinity is going to come from for that. And always a parenthesis on the infinities. So there we get our range out of that. Intercepts. X or Y intercepts. Maybe it's both. We got to look for both either way. So does this one cross the X or the Y axis? both, where at? What point is the only one that's on both? 0, 0. That origin is what its official name is, but 0, 0 is its ordered pair. Is this a continuous or discontinuous graph? Why? You got to pick your finger up to go to the next piece, right? Sometimes they connect. Not often, but sometimes they do. Okay, so this one would be discontinuous. Right. And again, with the calculator, you could do that. All that work to get it to graph it. X squared, parentheses, x, second math, is less than 2. We graph that. We see that part of the graph. It looks just like what we drew. And then y equals. Don't forget the parentheses. That's the key to this, is put those parentheses if you're going to use the calculator to help you. And then this one's a little easier because you just got the two straight up inequalities to greater than or equal to, which is 4. 2. And there we see that piece just like what we drew by hand. So you get those pieces out of that. All right. Because these two both went down to negative infinity, and then this one, it stopped its y values right here, but this one kept going with them. It was using they were using some of the same y values. Like up to this point, this left one and this right one were using the same y values. They're in different places, but same y values. And then this one ran out of y values, but this one was still using them, so we just kept going with this one. So really, it was this piece. Like I said, it's only two pieces that we used. This piece and that one.
Does it matter which one you use the water? Like, will it affect your answer?
It will if they're not using the same ones. Like if there were another piece that was kind of like stuck right here in the middle, then that you would have 3 pieces that you have to use. Okay, it's going to depend on the graph. Every one of them will be a little bit different. Okay. All right, let's look at one more thing with piecewise defined functions, and that's function value. And function value with piecewise is a little less complicated than the graphing. It's maybe I think a little more intuitive for that. So function value. Function value means find some value. Let's say f of -3, 4, and then it gives you this piecewise defined function. F of x equals, and then they throw this stuff at you. They say 2 plus x when x is less than 0, and then x cubed when x is greater than or equal to 1. Okay. It just asked us to find a function value. It didn't say find the domain, didn't say find the range, didn't do any of that other stuff. We're going to have to graph it to do this. All we've got to be able to do is look at that function notation and decide, okay, what is -3 even talking about? What is a -3 for this problem? Is it an x value or a y value? Right there. That notation says f of x. So anytime you have that -3 is an x value. We just got to know which piece do we plug that into. Okay? So to find out which piece that goes into, you say -3. Does it fit this inequality or this inequality? Is -3 less than 0 or greater than or equal to 1? Less than 0. So that means which piece are we going to use to find the value? That one. That's what function value does for us. Okay, so f of -3 would be 2 plus -3, which is -1. Because -3 fit in this inequality. You look for which inequality does the x value go with, and use that piece. Okay. If we were using the same function, For example D, and they ask us to find f of 8. Which piece does that fit in? 8. This number is 8 less than 0. Is 8 greater than 1? Yes. That means I'm going to use x cubed. So f of 8 is 8 to the third power. Which, if you hadn't done that with a graphic calculator yet, I'll show you how to do that. To the third power, or any exponent, type the number, hit the little housetop symbol. It's called caret symbol, just above the division symbol, and then pick your exponent. Hit enter. 512. Good thing we didn't have to do a graph. Way up there. So function value, plug into the piece that it fits with the inequalities. Gotta check your inequalities first. Plug into the piece that fits there. Okay? And that gets you piecewise defined functions. Okay. All right. One section down, 2 to go. I am just going to use regular paper for this, not graph paper. It's a lot of informational stuff. We're going to talk about some graphs. I'm going to graph some things on the graphing calculator instead of by hand, just because that's how you're going to do this. It didn't make sense to graph it all by hand. And you got that $100 machine in front of you that do it for you. And we're not really looking for values here. We're going to take a graph and shift it and move it and stretch it and shrink it, that sort of thing. So we're going to learn some rules about how that happens. So translations and transformations. Okay. All right. Y equals f of x. We know that y and f of x are the same thing. They mean the same thing. This is what we're calling the parent function. Okay, the parent function means that's what we're starting with. And usually it will be a very basic function like y equals x or x squared. They may just be generic and say y equals the function f of x. And it really doesn't matter what's going on. They're just going to ask you what translation or transformation happens if you add a 3 here. Depending on that, can do things. All right, so based on that, there are some things that can happen. There can be a vertical shift. And a vertical shift just means we take the picture of the graph. We don't stretch it or shrink it or anything. We just take a picture and we move it up a certain amount, whatever amount they add. Okay, that vertical shift looks like this. You take the parent function and you add some value. Or if you're moving it down, it'd be subtraction. That makes sense. Adding is up, subtraction is down. Okay, and anytime you see K is some number. It doesn't really matter what kind of number it is. That if it's a positive number, fraction, decimal, whatever. If we're adding it or subtracting it to the end, that's going to shift it, that parent graph up or down. Positive is up, negative is down. Okay. Vertical shift. We could have a horizontal shift. The way horizontal shifts look is you add on the inside, it moves it left. If you subtract on the inside, it moves it right. What we're going to see here with this, anything that's vertical is going to happen on the outside of the f of x or of the parent function. Anything that's horizontal is going to happen on the inside. So vertical shifts, vertical stretches and things are going to happen on the outside of f of x. Horizontal things are going to happen on the inside of the parentheses. That's what we're going to notice the pattern up here. But it's the opposite. You think when you're adding something, it's moving it this way, but it's on the opposite on the inside. And so it's like a mirror reflection of it. So if you add plus on the inside, then it's going to move to the left. Plus minus on the inside is going to move to the right. Okay, so gotta remember those things. All right, so that's on vertical shift, horizontal shift. Let's get a vertical stretch. Anybody ever play with silly putty when you were a kid? We used to do that all the time. We funny papers would come in on Sunday. You get your silly putty out, pat that stuff out, and you put it on, push down on Garfield, peel it up. Garfield's on the silly putty. And he transferred to the silly putty. Vertical stretch is like taking that silly putty with that picture on it and stretching it this way. When you did that, Garfield got skinnier, right, and taller. That's what a vertical stretch is. You take that graph. If it's an x squared function, it looks like that. If I stretch that vertically, then it's going to look skinnier. Like here, if I take that and stretch it, doesn't it look like it got skinnier? That's a vertical stretch. Mathematically, what's happening is you have some number times the whole function. And that number has got to be bigger than 1. That is a vertical stretch. If you're multiplying by a number bigger than 1, it's going to vertically stretch it. A number bigger than 1 vertically stretches. Okay? In the same idea, we could have a vertical compression. It was harder to do with a silly putty, but it could be done. A vertical compression, take that same picture. If I compress that vertically, it's pushing it down. So it kind of makes it push out a little bit. When you push that silly putty down, when you pressed it down, it kind of squished out the sides, right? So it kind of makes it look wider, okay? And it shrinks it, makes it shorter, okay? A vertical compression happens mathematically by taking, it looks a lot like that, except for the number is between 0 and 1. What kind of numbers are between 0 and 1? Decimals, small decimals, like less than $1. So 0.99, 0.01, 0.5. Any fraction equivalent of that, 1/2, 1/3. Those are all things that are between 0 and 1. So a vertical compression, vertical, remember, is happening on the outside. And if we're multiplying by something on the outside, we know it's going to be a stretch or a compression. If that number is big, bigger than 1, it's going to be a stretch. If that number is a small fraction or a small decimal, it's a compression. Okay? What we're going to have to do is take functions and recognize what happened, is what we're trying to do here. Okay? Now, that gets the vertical part of that. Let's get the horizontal part of that. Let's spell horizontal, right? Horizontal stretch. If you're going to horizontally stretch something, let's just take the quadratic, because it shows these things really well. A horizontal stretch would be taking that thing and stretching it like that. It looks a lot like a vertical compression does, but instead of squishing it down and making it shorter, it pulls it sideways. So it's like the silly putty taking Garfield and stretching him this way. Okay? Mathematically, what's happening with the equation is you're taking f and you're taking a number times x, or times the inside of the function. That number is got to be between 0 and 1. So it's a small fraction that you're multiplying by on the inside. Small number on the inside is a horizontal stretch. Small number on the inside is a horizontal stretch. So that means a horizontal compression is multiplying by some number on the inside that's a bigger number, that's bigger than 1. 1.5, 1.2, 3, 765. Any of those numbers are big numbers. If you multiply by a big number on the inside, it's a horizontal compression. Vertically, on the outside, big number stretches. Horizontal does the opposite, big number on the inside, compression. You may hear me slip up and say shrink from time to time. That was the terms that I learned in undergrad, stretch and shrink. But they've since changed the terminology to compression instead of shrink. But stretch, vertically, big number on the outside. Big number on the inside is a compression. Horizontal things are the opposite. Just like with the shifts, it was a plus on the inside. It moved it to the left instead of the right. It's the opposite of what you would think there. Okay, so horizontal things happen opposite ways. All right. 2 other things. A reflection across the x-axis. Y equals negative f of x. Something moves, this line here is the x-axis. If something moves from up here on the top of the x-axis above it to down here, what happens to the y value? If it's up here, the y value is positive. It moves down below the x-axis, what happens to the y value? It becomes negative. What's that doing? That's changing the y value to its opposite sign. Okay, so reflection across the x-axis is a vertical movement, so it happens on the outside, changes the sign of the y values. Okay. Last thing that we've got to recognize is a reflection across the y-axis. Y-axis, straight up and down, that's the y-axis. If something is on this side of the y-axis and moves across here, what happens? What value changes? The x value changes what? Signs. Okay? So to change the sign of an x value, that's horizontal. X values are horizontal. Y values are vertical. So that's going to be f of negative x. It's going to be a negative on the inside of the function out of that. Okay. These things are things you want to kind of memorize here. We're going to see some application of this in just a second. It's not so much that that's how you graph things. Really, the best way to graph things is plug in x values and work them out, get the actual points that goes with. But it's able to look at an equation and tell what happened to the parent function. Basically, that's what one of our goals for this particular lesson. All right, so let's look at taking it in one direction and then going backwards from there. So we want to write the equation for the transformation. Example A, our parent is f of x equals x squared. We're going to do several things to this parent function. The parent function is f of x is equal to x squared. Okay. Let's shift down 5 units. Okay. We're going to shift that down 5 units. We're going to have to do something to x squared. Shifting down 5 units, a vertical or horizontal movement? Vertical. So we know it's not going to happen to the inside on the x. It's outside. If it's vertical, it's on the outside. Shifting down 5 units is going to do what? Go back up here to our shifts. We had a vertical shift. If it's a vertical shift, you're going to take the parent function and add it or how many we're moving it. If we're moving down, we're going to do what? Subtract 5. So we're moving down 5. So our function then would be x squared minus 5. That's what we're after. With each one of these, go back to the original parent. It's not a building exercise. We're starting with x squared each time. Shift left 2 units. Horizontal or vertical? Horizontal. So anytime we see horizontal, we know that there's got to be some parentheses involved. What are we going to do to shift it left 2 units? Add 2. Good job. Not hard at all. Let's combine those. Let's say we shift up 6 and right 7 units. Up 6, right 7. Doesn't matter what order we do that in. We're going to finish it at the end. So if we got a vertical movement, yeah, the up. And we've got a horizontal one as well, right? So we know if there's a horizontal movement, I got to have some parentheses happening. What happens to x squared to move it right 7 units? Subtract 7 on the inside. And to move it up 6, you're going to add 6 on the outside. Not a hard thing here. We're not going to get anything super complicated with this stuff. We're just looking to, build some transformation ideas here. It's going to help us a little bit when we go to some stuff in chapter 4 and 5 with this. Number 4, going back to the original x squared. We're not building anything here. We're just going from there. Let's do a vertical stretch. By a factor of 4. Vertical stretch by a factor of 4. Okay. A vertical stretch is going to be a multiplier where? On the inside or outside? Vertical is going to happen on the outside always. So we won't need to put that in there with the x and the x squared. It's just going to be 4 and then x squared. The difference would be if you had a horizontal stretch, or let's do a horizontal compression. More similar thing by a factor of 4. A horizontal compression would be you multiply on the inside. With some functions, if you try to do this with a graph, it's easily confused because some horizontal compressions look a lot like vertical stretches. They look very similar when you graph them. So just having this rule set kind of in your brain is going to help you when you're just dealing with that. Because if you look at graphs, it's hard to tell. But when you look at equations, it's very easy to tell what's going on. All right, let's do this one. Last one for this particular example. Let's say we had a reflection. Not reflex, but reflection across the x-axis and shift down 4 units. reflect across the x-axis. What's that going to do? Make it negative. So that's a negative x squared. And then if we shift that down 4 units, what do we do next? Inside or outside? Good. Vertical, so it's on the outside. If it were a horizontal shift, we would have to erase that squared, put a parenthesis set around it, and then put our +4 on the inside. If it was left or right, depending on if it is left or right. Okay. All right. Let's do one of these. Example B. Two 6 is a point on the graph f of x. What would the ordered pair be on y equals -3 parentheses, or excuse me, f of x minus 1? These are, I would say, the most difficult problems out of this section, is being able to do this. Take an ordered pair and move them. But it's not hard if you don't think about the ordered pair until you decide what transformations are happening. Okay? What transformations are happening here? Okay, so we're going right 1 across what? That negative back on the outside there tells us x-axis. Because it's on the outside, it's going to be the x-axis. What does the 3 do? That's the only part we hadn't used yet. Vertical stretch. All right, now get those transformations listed. Then you take that and say, okay, if I move this point to the right 1, where does it go? Just right 1. I'm just doing one piece at a time. Be 3, 6. Doesn't go up or down any for that first part. I'm going to go 3, 6. Okay. So after I move right 1, it just moves the x value to the right 1, which would be the 3. 6 stayed the same. This says reflect that across the x-axis. What does reflecting across the x-axis do? So 3, 6 is up here, going down here. So what part gets negative? The 6, not the 3. So that new ordered pair would be 3, -6. Then it has a vertical stretch. What does a vertical stretch affect? X values or Y values? Use the vertical. Which values are vertical? Y values are vertical. Good. So the Y value is the only one that's going to be affected by this vertical stretch by 3. So what's -6 times 3? -18. So the final ordered pair would be 3, -18. Notice we started on the inside. Think about order of operations. Parentheses come first, then exponents, and then all of multiplication, division comes last. What would be last? The negative we took care of with the reflection. So we were only using the 3. The negative, if you've got to almost say, okay, I'm separating the negative sign from the number there. And it's treating those as 2 separate things. Because if you use it, you can accidentally use it twice. If you multiply it by -3, it would be positive 18. But we've already used the negative to get the reflection. So we're just using the 3 to get the stretch. Let's do another one. Let's move it with this function. Y equals f of x plus 4 and then minus 8. So doesn't matter what the function was. We're moving the point 2, 6. That's the point we're moving based on these transformations that are happening there. What transformations do we see happening? Which way? Left 4. So if I move 2, 6 to the left 4, where's it going to end up? Left 4, not right 4. Be -2, 6, right? What does the minus 8 do? Down 8 units. I take -2, 6 and I move it down 8 units. Where's it at? -2. So the ordered pair is in -2, -2. The key is get your transformation and then do that to the ordered pair. Don't try to overthink and do it all at once. Do one transformation at a time. Start on the inside of the parentheses if there's anything happening there, and then work your way up. Yes, ma'am. That's right. It's a vertical shift because it's on the -8's on the outside, so that tells us it's a vertical. So that's how we know to do that to the y value and not the x value. Remember, vertical things happen on the outside; those affect y values. Horizontal things happen on the inside; those affect x values. And remember those things. That's going to help you with this transformation stuff. Okay. All right. That's the end of chapter 3. Okay. And we're going to get one section in chapter 4 to start off, and then we'll be able to finish chapter 4 next week after that. So we've got one more section to cover. Just some regular paper will be fine with this. We're going to do some stuff with linear equations. So this is the easiest section in chapter 4 that we'll cover. We'll do next week. We'll get into quadratics and combination of linear and quadratic together, that sort of stuff with chapter 4. Chapter 4 is kind of a review of all the different kinds there. Then chapter 5 gets into higher degree polynomials. So linear functions. Linear functions, normally written in this way. You may be more familiar with our old friend, y equals mx plus b. We usually use function notation f of x. That's how you're going to normally see it here. Okay. The m is the what of the equation? The slope. B is the y-intercept. That stuff hadn't changed since 7th grade. It's all the same. It's still the same linear equation we've been dealing with forever. Boring stuff. Okay. So we'll start off with find the function value. Say we have f of x is equal to 3x minus 7 and they want us to find f of -2. I talked about this when we were talking about piecewise defined functions, but it was piecewise then. We're dealing with linears here. This is easier. What do we do? Yeah, plug -2 in for x. 3 times -2, and then subtract 7. Order of operations still rules the roost, so multiplication happens first. -6 minus 7, -13. So what that creates is an ordered pair for us too, or -2, -13 is the ordered pair that goes with that. But we're just finding function values, just plugging in x. Nothing fancy about that. Okay. Let's move on to something a little more fancy. G of x is equal to 2/3 x plus 5. And we want to find the intercepts. Okay? Find the intercepts. What kind of intercepts are they talking about? X and y. Okay? The y-intercept, because it's a linear equation, should be the easy one. Okay? So we're looking for x-intercepts and y-intercepts. Okay? X-intercepts are tougher than y-intercepts. What's the y-intercept? What's the ordered pair for that? 0, 5. Yeah. We get that because that's what B is. We know B. There it is. It's spelled out to us. Because it's a linear equation, we get that. How do we do that algebraically, which will lead us into what we're going to do next one? How do I get this ordered pair from that function? What do I plug in where? Well, look at the ordered pair. If I plug in 0 for x, I'll get a y-intercept. That works with any kind of function. It's simpler in linear functions to just look, oh, I know the b is y-intercept. I know that already. It's a memorized fact. But with any type of function that we encounter throughout this whole course, if you need a y-intercept, plug 0 in for x and you'll find it. That's going to work every time. When we get to next week, we get larger functions to deal with. We need the y-intercept, we just plug 0 in for x and we got it. Okay? Now, defining the x-intercept, how do we do that? No, that would get me where it's equal to 5. Say what's equal to 0? Yeah. What we're really doing there is an x-intercept on the x-axis. We look at the coordinate plane. Any point that's on here, the ordered pair, the y value is going to be 0. So what we're doing there when we set that whole problem equal to 0 is making y 0. To get a y-intercept, you make x 0. To get an x-intercept, you make y 0. Okay? Plug that in, solve it. Subtract 5, we got -5. So 2/3 x equals -5. How do we solve that? Good old algebra review here. Good job. Doesn't work out real pretty there, but that's okay. -15/2. I'm going to leave it in proper fraction. So our x-intercept as an ordered pair would be -15/2, 0. And those are my only intercepts. If I wanted to check that, I've got that $100 paperweight there. I can graph that equation, 2/3 x plus 5. And then to check those places, I can hit trace, and then it was -15/2. That's what I thought was the x-intercept. Hey, what do you know? 15/2 is -7.5. And the y value is 0. That's the right one. I want to check the y-intercept. We're pretty sure we got that right, but I'm going to check 0 just to make sure. Hey, there it is. Y is 5. So that's always a checking thing. You can always make sure you got it right. When we get to more complicated functions, that's a little more helpful. Okay. Linear stuff, it's pretty simple, but it's always good to have a checking place. All right. Let's get an exceptional one here. Example C. H of x is equal to 8. H of x is equal to 8. Ooh. What does that even look like? Honestly, I don't know. So let's go to the graphing calculator and get some help. H of x is the same thing as y. So I'm just going to graph y equals 8. Horizontal line. What's the slope of that horizontal line? Yes. Slope is 0. Does that thing have an x-intercept? No, there's not one. Does it have a y-intercept? Where at? 0, 8. Those, I throw that in there because that seems to be something that's easily forgotten because you don't do much with constant functions in high school algebra, or don't do a ton with it in this class either, but every now and then they'll throw that in on that final exam and just say, oh, do you remember this? It's the easiest thing you've ever done, but you can't remember it because you never do it, kind of thing. So I always kind of try to throw that in. All right, let's look at the next thing is the average rate of change. Fancy, big, long name for slope. That's all it is. Average rate of change is slope. In your book or anywhere you look up college algebra things and they talk about the average rate of change, they're going to use these fancy things. Delta y over delta x. That means change in y over change in x. And they'll use this formula to confuse you. They'll say f of a minus f of b over a minus b. All that means is f of a is a y value when x is a. F of b is a y value when x is b. A and b are just the x values. We remember from high school math this formula. M equals y2 minus y1 over x2 minus x1. Right? That's the one I teach in my high school classes. Okay? That's the same one. It's just not as fancy, but it does look fancy. It's average rate of change. It's slope. It doesn't mean anything new. Okay? All that stuff is fine. All right. Next thing we want to do is take some data, use the average rate of change to help us write a linear equation based on that. Okay, so we're going to write a linear equation for given data. And they might have a big long story problem that goes with this. I'm just going to give you the table of information. X values, Y values. 20, 50, 30, 47.5, 40, 45, 50, 42.5, 60, 40, and then throw one in there. 70, 37.5. Okay, so all of those fun numbers there came from something. I don't know. They told us to write a linear equation. So that part tells us what's going on. So what I'm going to do is I'm going to pick two ordered pairs to write a linear equation for that one. I'm going to pick the ones that don't have decimals because that's easier. If I get to choose, I'm going to pick things that make my life easier. So I'm going to use those two ordered pairs. Okay. So I'm going to first find the slope. y2, I'm going to use 50 minus 45 over 20 minus 30. Notice that I didn't pick the second one to start off with because it doesn't matter. Okay? I'm not 30, I should have wrote 40. 20 minus 40. That's the x value of that. That's red was. It doesn't matter what y value you start with as long as you start with the x value that goes with it. Okay? If you wanted to start with 45, you'd have to start with 40 as the x. So it doesn't matter as long as your ordered pairs are vertically lined up. Make sure of that. Work that out. 50 minus 45 is 5. 20 minus 40 is negative 20. So that reduces to negative 1/4. And then you start with the slope-intercept form of the equation. The only problem is we don't know what the y-intercept is. We've got to find that. So then you pick one of your ordered pairs to use to find the y-intercept. I'm going to pick the 20/50. I'm going to plug 50 in the place of y, 20 in the place of x. B is now the only variable in the problem. So I've picked an ordered pair from my data, one of the two that I use to find the slope. Doesn't matter which one I pick, I'll get the same answer no matter what. Okay? Plug that in for x and y, because it's an ordered pair. 1/4 of negative 20 be negative 5. Add 5 to get b by itself. 55 is equal to b. My final answer, y equals negative 1/4 x plus 55. That's the equation for that data set. A linear model for that particular data set. All right. Last thing, get out of here. Two functions, f of x equals 3x plus 5. G of x is equal to negative 1/3 x plus 1. Okay. Two functions. We want to answer some questions about those. I guess I should write a little more context here. Where is f of x equal to g of x? We've got two functions. Have to be both be linear in this section. We'll get to the others. They may mix and match some of the quadratics and linear, something like that. But it wants to know, the first question is, where is f of x equal to g of x? Okay? Well, looks like an equation to me, doesn't it? What can I do to get something where I can work it out? I know what f of x is. It's that. I know what g of x is. It's that. Could I not just set those things equal to each other and solve it for x? And I get the where. That's what I want to do. Okay. So algebraically, I can do it this way. 3x plus 5 equals negative 1/3 x plus 1. And I do algebra on that. Solve it for x. So I'm going to add 1/3. And that's going to give me 9/3 plus 1/3 is 10/3. X plus 5 is equal to 1. And then I would subtract 5. It'd be 10/3 x equals negative 4. Flip and multiply. And there I have x equals negative, okay, I can cross cancel, 6/5. That is where f of x is equal to g of x. is at the x value, negative 6 over 5. That's doing it algebraically. We can do it with a graph as well. If we graph those two equations, where they're equal to each other, it will be where the graphs do what? Cross. That's exactly right. So, show you how you can do that with the graphing calculator. Not always the best method, but a great way to check in case you weren't sure. So 3x plus 5. Doesn't matter which one you put in, y1 or y2. The second one is negative 1/3 x plus 1. If I graph those two, there they show up. Okay. Right there is where they're crossing. Very difficult to guesstimate where that's at. I think it is at negative 6 over 5. I could hit trace and type in negative 6 divided by 5, and I get 1.4. Notice that it says y1 up here. If you got the colored one, it'll be in that color for whatever graph you're on. If you got the black and white one, it's just going to tell you y1 up here. It tells you that's the function that's on. If I press the up arrow, it'll swap to y2. Notice, same decimal there. Not quite exactly the same. That may not be the best way to go about it. There is a better way with the graphic calculator to get that intersection. The way to do that is to hit second and trace and get the calculate menu. And we can find out where these two intersect by using the fifth option, intersection. Number 5. First curve, just hit enter. Second curve, just hit enter. And then it says guess. And what the reason you want to guess is because when we get to more complicated problems, you might have a quadratic and a linear one, and they hit twice. So it needs to know which one are you talking about. This one, there's only one place that they cross, so you don't have to be exactly right on it. But I always move my cursor over close to where they cross at. If I'm dealing with the more complicated functions, then I need to move to the place they cross at because they may cross at more than one place. So I need to tell it where I'm looking for. I'm looking for it right there. Negative 1.2, that's the decimal for negative 6 over 5. The y value is 1.4. That's what we saw when we hit trace with the blue one. And we're on the intersection there. So that tells us we did it right. So that's one way to get the intersection, or where those two equations or functions are equal to each other. A little more difficult question would be, where is f of x greater than g of x? Same two functions, 3x plus 5 and the negative 1/3 x plus 1. But where is that inequality happening? How do we do that algebraically? I mean, solving. Can we solve an inequality? We set up the inequality just like we did the equation, right? It's going to give us that stuff going on. So I would set that up. F of x goes first. That was 3x plus 5 is greater than negative 1/3 x plus 1. And I'd solve it the exact same way. Add 1/3. That's 10 over 3x plus 5. It's greater than 1. And I would subtract 5, just like I did when I did the equation. And then the last step would be multiply by the reciprocal, 3 over 10. Negative 6 over, it's when x is greater than negative 6 over 5. We would expect that because that's the same answer we got when we set them equal to each other. If we look at the graph, where is f of x? F of x is the blue one. G of x is this other one. Where is f of x greater than that? That means where is f of x above the other one? That would be from here, positive infinity. Everywhere from that point on up. It's not including that point because that point is where they're equal to each other, and our inequality didn't have an equal to mark. Okay, so it starts here at -6/5 and goes to positive infinity. That's where that f of x is greater than g of x. If it asks where is g of x greater than f of x, well, it should be right there. Negative infinity up to that point. And we could solve the inequality the same way. It doesn't change that at all. Okay, so all that stuff is staying the same, but as far as how you would solve it, your inequality just changes. Okay, all right. Give you a little heads up on some problems that you might want to look at in these sections. I'll start from the back. 4.1 is on 284. The first 50 problems in that section. And then, hold up, back up. Sorry, wrong edition of the book. It's 287 in the new edition. 13 through 49. I would just, some of the odd ones out of that, some out of each section. 3.5 is on page 264 in the new edition. There, 7 through 65. And then 3.4, the first section we talked about was page 252, 11 through 51. Exclude. Don't worry about number 47. It's a doozy. And don't worry about it. So if you're looking in the book to do some practice, skip on 47. It will do nothing but frustrate you and you won't gain much from it. There you go. Okay. All right.